what is hypothesis about a population and what is the purpose of hypothesis testing. You have a population, say some normal population with mean mu and variance sigma square. And suppose it is given that value of mu is mu0, and let's say variance is also given to you exactly sigma 0 square. So what I'm saying, you have a normal population with mean mu0 and variance sigma 0 square. Now suppose you suspect that population mean is not mu0 due to some reason. So what is the existing statement about the population? That mean of the population is mu0. Prevailing statement or existing hypothesis that you call null hypothesis. Existing statement or prevailing statement about the population is null hypothesis. So basically we want to test S0, whether S0 is true or not. So we have some statistical methods to do that, and that is called hypothesis testing. So how we do that, we set up alternative hypothesis. In this particular case, what is alternative hypothesis? Mu not equal to mu0. A hypothesis complementary to the null hypothesis is called alternative hypothesis. Okay, so how to test whether HA is true or not? So what we do, we choose a sample from the population, and on the basis of sample information, we decide the truth of HA. And alternatively about S0, of course. So let's say we choose a random sample, x1 to xn, of size n from the normal population, and also assume that its mean is x bar and variance is s square. So from your random sample, you can say the small x bar is the observed value of the sample mean. In general, x bar is a random variable, you know that thing. So let's say this is the observed value. Now, you know this result if this random sample is taken from the normal population. Then the statistic x bar follows again a normal distribution with mean, same mean mu or mu0, and variance sigma 0 square over n. You know this result. If the random sample of size n, this is taken from this normal population with mean mu0, variance sigma 0 square over n, then the statistic x bar follows normal distribution with mean mu0, variance sigma 0 square over n. On the basis of this information, can we write 100 into 1 minus alpha % confidence interval for x bar? See carefully, I am asking you 100 into 1 minus alpha % CI for x bar, not for mu. Mu is given to me, mu is mu0. Can we do that? Let's do that. Because x bar follows normal distribution with mean mu0 and variance sigma 0 square over n, so probability of x bar lying in the interval minus z alpha by 2 to plus z alpha by 2 probability of x bar minus mu 0 over sigma naught divided by root n. Probability of this statistic, it is normal random variable, standard normal random variable. So probability of this standard normal variable lying in the interval minus z alpha by 2, 2 plus z alpha by 2 is 1 minus alpha. You will agree with this. Let's simplify it further. I need 100 into 1 minus alpha percent Ci for x bar. So what I need to do, just cross multiply by sigma 0 over root n and then add throughout mu 0. So I can write mu 0 minus sigma 0 over root n into z alpha by 2 to mu 0 plus sigma 0 over root n z alpha by 2 equal to 1 minus alpha. So finally, what is 100 into 1 minus alpha percent Ci for x bar? In the middle, it is x bar. What is 100 into 1 minus alpha percent Ci? For simplicity, you can write mu 0 plus minus sigma 0 over root n z alpha by 2. And geometrically also, you understand what is this interval. Population is normal. Z alpha by 2 is this value minus Z alpha by 2 is this one. So in this tail, how much region? Alpha by 2. This side also alpha by 2. So you understand this thing, okay? My main interest is to find 100 into 1 minus alpha percent Ci for x bar. Means the observed value of x bar, Ci is this. Please make a note of this. We will use it for hypothesis testing. You will understand how. For understanding, let's choose alpha equal to 0.01. Then what is this 100 into 1 minus alpha percent Ci? Mu 0 plus minus z sigma 0 by root n z 0.005. What does it mean? Understanding its meaning is very important at this stage. It means, I'm writing it explicitly, there are 99% chances of observing x bar in the interval mu 0 plus minus sigma 0 over root n z 0.005. Note down this line. That is the meaning of confidence interval. It means there are 99% chances of observing the x bar value in this interval. If the population mean is given mu 0, standard deviation is given sigma 0, and the sample is of size n, then there are 99% chances of observing the sample mean in this range. That's the meaning. Now, I'm suspecting the population mean, right? I believe that mu is not equal to mu 0. So what can happen? The observed value of test statistic may go outside this interval. Otherwise, also it can go outside this interval. It's 99% Ci. But if mu is not mu 0, certainly it is a very good possibility that this observed value of x bar means this. You can also denote it by x bar observed. lies outside this interval. Understand this point. Here is the main concept. If you choose a fair sample, this side it is 99%, so it is 0.5%. This side, because of symmetry, 0.5%. Half a percent. Okay. If you, let's say, mu 0 is the true mean of the population, then it is for sure that there are 99% chances that observed value of the sample mean lies in this interval. 99% chances, it's a big probability. Only 1% chances are there that the observed mean can go in this region or this region. Means greater than mu 0 plus sigma by root n z 0.005 or less than this one. You understand this, okay? But if the population mean is not mu 0, actually it is not mu 0, then there are chances that it can go in these regions also. So let's set up this level. Let's test, let's see how we design our hypothesis. Let's say alpha is 0.01, means we are saying that there are 99% chances of the population mean to lie in this interval. If the observed value of the sample mean goes outside this range, outside this interval, I will reject this null hypothesis. What is my null hypothesis? Mu equal to mu 0. What is alternative hypothesis? Mu not equal to mu 0. So what I'm designing from my side, that if my observed value of the sample mean lies in this range, which range? That I have set up with 99% confidence, this range, or you can say this interval. Let's call, just for simplicity, let's call this interval or this region as H0 region. Means if the observed value lies in this range, means in this interval, then we cannot reject as 0. But if the observed value of the test, this sample mean lies outside this interval, means this region or this region, let's call these regions HA region. These are also known as critical regions, or you can say rejection regions of H0. There are many names. You should understand any one of them. This is called this region or this region. These two regions are called critical regions or rejection regions of S0. For simplicity, I'm calling this region, the interval, this one, I'm calling this as H0 region. Complement to this or this, I'm calling HA region. So I'm saying that if my observed value of sample mean lies in the HA region, I will accept the alternative hypothesis. Okay. If my observed value doesn't lie in HA region, let's say it goes into H0 region, then I will not be able to reject H0. Then I will not be able to reject as 0. It doesn't mean that I will accept as 0. Because here I am taking 99% region. Okay. Okay. Let's say my observed value of the test statistic lies in this critical region, here or here. Let's say it lies here. Something X bar observed lies here in the critical region, or you can say rejection region of S0. Then what will be my conclusion? At 1% level of significance, I am rejecting S0. Understand? What does it mean? Why I say 1% level of significance? Because I'm 99% confident that H naught is not true. But 1% I'm not confident because a particular sample may have mean in this region also. This is 1% region of the original hypothesis. So please note this line. If the observed value of the test statistic lies in this critical region or 1% region of the alternative hypothesis, then we accept as zero at 1% level of significance. That means I'm 99% confident of rejecting as zero the null hypothesis. It's very important to note. That's how you will understand the meaning of type 1 error. This alpha is in fact type 1 error. Why it is called type 1 error? Because it is possible that true mean is mu0 and by chance the sample mean, the observed sample mean value lies in this HA region. Still it can lie, but there are only 1% chances of happening this. So if HA is not true and we accept as HA on the basis of our observed value, then what we have done type 1 error. But happening of this, what are the chances of happening this? Only 1%. So in that case, we have done only type 1 error, means only 1% error. That is called type 1 error. So you can note down one line for type 1 error. Probability of, please note this line, I'm speaking. Probability of accepting HA, let me write it. Probability of accept HA when HA is not true. Is called type 1 error. Okay, and what is this? Alpha. That we set from our own side. If we don't set, we can calculate it using this. Accepting HA when it is not true. So we have set up very low risk, 1% only. So type 1 error is under our control. Hope up to this it is fine. Let me repeat again. You have a hypothesis for testing. Let's say it's population mean. The prevailing hypothesis is that population mean is mu0. But you suspect that it is not mu0. So alternative hypothesis is HA equal to mu not equal to mu0. How to test it? At what percent or at what level of significance we can test it? Set up a level of significance, say alpha equal to 0.01. That means level of significance is 1%. What does it mean in principle? Actually, the observed sample mean has this interval as 99% confidence interval. Okay, so if your observed value of the sample mean lies in this interval, then you cannot accept HA. If it lies outside this, then you can accept HA. But note that we never accept H0. In case our observed value lies in the H0 region in this interval, then we say that sample data is not enough to reject as zero. We never say that we can accept as zero. Acceptance happens only for HA, because accepting as zero could be a very big risk, and that is called type 2 error.
Excuse me, sir.
Yes.
Sir, can we say alpha is the level of importance given to alternative hypothesis?
Yes. Of course, alpha is setting, what is alpha? That we are setting from our side. We are taking this much risk.
Okay.
Okay.
So it is 99% confident that we are accepting null hypothesis.
No, that we cannot say. That's what I'm telling you. No, 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 no. We are not accepting as zero. We are rejecting as zero.
Sir, but
I'm,
99% confidence.
but you are observing a single value there in a big region. Your sample is a single value, isn't it? Observed sample mean is a single value.
Yes,
And
sir.
you are searching that in 99% region. Of course, it can be there. But that doesn't make the basis of accepting as zero.
Yes, sir.
But if you observe the value in this 1% region, 1% probability region, then certainly you can suspect that mu is not equal to mu zero. In that also there is a risk, but that is of 1% only.
Yes, sir.
Okay, you will understand it. Just keep on listening. All right. So I was
Sir, I
explaining.
believe,
Yes,
sir, type 1 error is rejecting H naught when H naught is true.
it's same thing.
No, sir. You have switched type 1 and type 2 errors. Type 1 error is rejecting H naught when H naught is true, not accepting H naught when H naught is true.
What does it mean? Is it not same thing or something different? What I've written? You are accepting HA when HA is not true. If suppose, okay, let's understand it like this. Suppose HA is true and you have accepted it, then you have not done any error, isn't it? You can write in terms of H naught also. H naught is true and we have not rejected it. It's the same thing.
Sir, HA is the alternative hypothesis. Okay.
HA is the alternative hypothesis, yes. Okay, let's see type 2 error. Fail to reject. Fail to reject as zero when it is not true. Fail to reject as zero when it is not true. This is a big risk called type 2 error denoted by beta. Let me tell you here itself how to calculate type 2 error. But before that, please note this region, this interval, Ci for observed value of x bar. What is it? H naught region. Opposite region means outside this interval, this side or this side. What is it? HA region. You can call it critical region or you can also call it acceptance region of HA. What are these boundaries called? Critical points. Boundaries of the CI are called critical points. Okay, after noting down these points, you can see further how to calculate type 2 error. Type 2 error is probability of, you can say x bar in the, I'm writing roughly, okay? You just to make you understand. Observing x bar in the CI of x bar. Which CI? When H naught is true. Means when mu equal to mu zero. But assuming that, okay, What is your alternative null hypothesis? Mu equal to mu 0. But suppose that actual population mean is something mu equal to mu 1. And let's say you, due to your observed sample value, you have failed to reject as 0. So how much error you have done in that process, how to calculate that, that is beta, called type 2 error. So what I have written, observing x bar in the CI of x bar in the original CI of x bar, let me write it simply in the CI of x bar, but assuming now mu equal to mu 1, because this is the true value of the population mean. When we will do an example, you will understand, but let me explain further. I'm trying to say that probability of observing x bar in which interval? What is the original interval for the population mean? Mu plus minus, not population mean, sample mean, mu plus minus z alpha by 2 sigma by root n. Probability of observing in the observing x bar in the H naught region, but now assume that mu equal to mu 1. Means your calculation will be done by assuming the actual given mean. This probability is called type 2 error. Just note down this formula. When we will do a problem, you will understand. So I have already explained you that how to set up level of significance and how to do the hypothesis testing at the given level of significance. Means alpha will be given to you in the problem. Okay. Considering that alpha, calculate the CI of the statistic that can represent the given situation. I will tell you what are the different statistics that we use in different problems. After that, just once you know alpha, then you can calculate CI of your test statistic. If the observed value of the test statistic lies in the CI, then you cannot accept the alternative hypothesis. Okay, you will simply say that the given sample or given sample is not enough to reject as 0. But if the observed value of your test statistic lies outside the H naught region, you can accept the alternative hypothesis at the given level of significance. There is one more way that you can avoid calculating the CI of the test statistic. Note down that also this is second way for hypothesis testing. There is a term called p-value of the test. What is it? I'm taking in this explanation example of x bar, but it could be some other test statistic also. Okay, probability of observing x bar, either greater than mu 0 plus, what is that interval? Mu 0 plus z alpha by 2 sigma by root n, or no. You have some observed value of x bar, right? Observed value. Probability of observing x bar greater than observed. Okay, let me write it like that. Then it's very simple. Probability of observing x bar such that mod x bar is greater than x bar observed. What does it mean? You should understand it. This is the normal distribution. Let's say this is x bar observed. What I'm telling you, probability of observing capital X bar either greater than plus x bar or less than minus x bar observed, this side or this side. This probability is called p-value of the test. Okay, if p-value is less than alpha, then accept HA, accept HA. Otherwise, don't accept HA. Just note down this formula for calculating p-value. If p-value is less than alpha, then accept HA, otherwise don't accept HA. It's a very simple thing. You should understand why this happens. You know, this is alpha by 2 region, this side alpha by 2 region. If x bar observed is greater than this alpha by 2 value, only in that case sum of these two regions would be less than alpha. It means your observed value of the test statistic lies in the critical region, the acceptance region of HA. Okay, but if it is greater than, then somewhere here means less than this alpha by 2 value, it will be in the H naught region. Main thing is that. Okay, you will realize it when you will do the problems. Right now, just note down this formula. So we have two options for hypothesis testing. Number one, just find CI of the test statistic and see whether the sample observed value of the test statistic lies in the CI or not. If it lies outside, you can accept the alternative hypothesis. Otherwise, you cannot accept the alternative hypothesis. Acceptance is only said about the alternative hypothesis. H0 is never accepted. Okay. Second way is calculate p-value of the test. In this particular explanation, I am taking the sample mean statistic. Okay. There are other statistics also I will explain. So in this case, what is the formula for calculating p-value? Mod x bar greater than x bar observed. So if the p-value of the test statistic is less than alpha, then you can accept HA. Otherwise, you cannot accept HA. What is type 1 error? Alpha is type 1 error. What is type 2 error? When we fail to reject S0, when it is not true. Type 2 error is calculated with respect to some given alternative of the population mean in this case. So we'll do problems on this, then you will really understand that how to calculate type 2 error.
Sir,
Yes.
so in the second last expression where we have defined beta, which
Yeah.
mu should we take for the expression x bar belonging to
Yes. Yeah. In this case, the original CI, as I said, original
okay,
CI you have calculated, right? Already.
the mu naught, using mu naught?
Using mu naught, yes.
Okay, sir.
But then you will convert that to the standard normal variable, then you will use mu1. We will do
Fine,
a
sir.
problem. Don't worry. You'll understand. Okay, so these are the basic things. Now, I'm going to write something very important for you, very shortcut. Note down these things because these are not in the online notes and not in the textbook also. So it is better you note down all the points. Now the thing is that which kind of statistics we need to consider in different problems. So I'm covering all types one by one. Just note down them. Types of the test statistic. First is 100 into 1 minus alpha percent CI for x bar. Small x bar, you know its observed value. Let's say sample size is n. A random sample of size n is taken from the population with mean x bar And let's write variance also. Variance of x is s square. S square is the object value of s square. Then one case we have already calculated. What is that? The 100 into 1 minus alpha percent Ci is mu plus minus z alpha by 2 sigma by root n when you have taken your random sample from a normal population with mean mu and variance sigma square. This case we have already done. Okay, we have derived it. Or it could be a non-normal population with mean mu, variance sigma square, but in that case sample size should be at least 30. You can apply this in these two cases. Either it is a normal population with non-mu and variance sigma square, or it is a non-normal population with mean mu sigma square, but in second case you have to ensure that sample size is greater than or equal to 30. You know that it happens because of the central limit theorem. Second thing, for x bar, if you choose your sample from a normal population with mean mu, or it could be non-normal population also. Thing is that sigma square is unknown. In that case, you have to ensure that sample size is greater than or equal to 30. In this case, what is 100 into 1 minus alpha percent Ci? Mu plus minus z alpha by 2 s over root n. Means we use this sample variance in this case. Point is that if population variance is not given to you, only population mean is given. So it could be normal population or it could be non-normal population. In both cases, you have to ensure that n is greater than or equal to 30. Then you can use this Ci for x bar. Third possibility. If the random sample is coming from normal population with mean mu, again variance is unknown, but let's say sample size is less than 30. Then what is Ci? Mu plus minus T alpha by 2. T alpha by 2 S over root n. You know when sample size is less than 30, means small sample, population is normal. Then it has a connection with, then x bar follows which distribution? T distribution with n minus 1 degrees of freedom, if you recall. That's why this is the Ci. Okay, these are three cases for x bar. Now, 100 into 1 minus alpha percent Ci for difference of population, difference of sample means. Let's say the observed value is x1 bar minus x2 bar. What is it? Mu1 minus mu2 plus minus z alpha by 2 sigma 1 square over n1 square plus sigma 2 square over n2 square. Can you use it? Means you have two normal populations. Normal population 1 with mean mu1 variance sigma 1 square. Normal population 2 mean mu2 variance sigma 2 square. Means you have taken two samples from two different normal populations with mean mu1 mu2 variances sigma 1 sigma 2 square. Sample sizes are n1 n2. In that case, this is the Ci 100 into 1 minus alpha percent Ci for the difference of sample means. Then 100 into 1 minus alpha percent CI for sample proportion P cap. Let's say small p cap is the observed value of capital P cap. If you recall, if you choose a random sample of size n from a binomial population, then p cap is defined as x over n. X is the number of successes. All that stuff. Hope you recall. Then what is 100 into 1 minus alpha percent Ci for p cap? It is p plus minus z alpha by 2 square root of p into 1 minus p over n. In this case, we are choosing the random sample from a binomial population with parameters np. So n and p are given to you. You are looking for Ci for observed proportion of the sample. Noted? One more thing, sometimes in hypothesis testing, we need one-sided thing. Means, suppose your hypothesis testing is something like this. H naught is mu equal to mu 0, or you can say mu less than equal to mu 0, and HA is mu greater than mu 0. In that case, you will be interested in the right tail only. The right tail means you will leave alpha percent region from one side only. So you need to consider only upper bound of your CI. So in that case, this formula changes to simply Z alpha by T, you can write Z alpha. You need not to consider minus in that case. Only mu plus Z alpha times sigma by root n. If you are applying a right tail test, you will see the examples. Sometimes we need right tailed, sometimes we need left tailed also. Left tailed, you understand this similarly, just consider mu minus Z alpha sigma by root, and in that case you are leaving alpha percent region to the left. I think you have done one-sided confidence bounds. Okay, it's the same thing. All right, I think you have noted all this. I need to write down 2 more points, then we'll go to the problems. The approach I'm using is very simple and different from the textbook solution, but you'll get the results very easily, especially when calculating type 2 error, you will find it very easy. Okay. Note down further 100 into 1 minus alpha percent Ci for difference of sample proportions from two different populations. Let's say the observed value is small p1 cap minus p2 cap. What's it? It's similar, you can write it easily. P1 minus P2 plus minus Z alpha by 2 square root of P1 into 1 minus P1 divided by N1 plus P2 into 1 minus P2 divided by N2. So in this case, you have taken 2 samples from 2 different binomial populations with parameters N1 P1 and N2 P2. These are sample proportions. So we are looking for Ci for difference of sample proportions. So this is the Ci. Final 100 minus alpha 1% Ci for sample variance. You know this is related to chi-square distribution. So I'm writing the 100 into 1 minus alpha percent Ci. Sigma square over n minus 1, chi square 1 minus alpha by 2, comma, upper limit is sigma square over n minus 1, chi square alpha by 2. In chi-square, you know, chi-square distribution is not symmetric. So you have to calculate both the limits separately. You cannot do plus minus. Noted? Now go to the online notes and see page number 34. Example on page number 34. I'm reading the statement. You also listen and read the statement, but don't see the solution there. I will not follow that approach for the solution. So you also should not see that solution. Just read the statement. The statement of this example is a manufacturer of sprinkler systems used for the protection in office buildings claims that the true average system activation temperature is 130 degree Fahrenheit. True average system activation temperature is 130 degree Fahrenheit. A sample of size 9, or you can say a sample of n equal to 9 systems, when tested, yields a sample average activation temperature of 131.08 degree Fahrenheit. Okay, this is the observed thing. If the distribution of activation times is normal, means the given population is normal, with standard deviation 1.5 degree Fahrenheit, do the data contradict the manufacturer's claim at significance level alpha equal to 0.01? First, see what's given to you. A normal population with mean 130 degree, in our notations it's mu0, it's given to you 130 degree. Sample of size 9 is taken, n is 9, and observed sample mean is 131.08, means x bar, small x bar value is given to you, it is 131.08. After that, population standard deviation is also given to you, sigma 0, or you can write sigma. It is 1.5. You see, the manufacturer is claiming that average system activation temperature is 130. This is the manufacturer's claim that we want to test. Means mu is equal to mu0, 130, according to the manufacturer. To test this claim, what is done? A sample of size 9 is selected from the population. So what is alternative hypothesis here? Mu not equal to 130. For testing this, what is done? A sample of size 9 is selected, and what is observed? Sample mean is 131.08. What is asked from us? At this level of significance, see whether manufacturer's claim is correct or not. So you should understand which statistic will work here, what kind of population is given, which CI we should use to test this claim. Clearly, the sample is taken from normal population. And for this normal population, both mean and variance are given. So see the list that you have noted. Which case is applicable here? The hypothesis is about the population mean. So the first case itself is applicable. Means which formula? mu 0 plus minus, or you can write mu, it's up to you. Mu plus minus z alpha by 2. Alpha by 2 means here 0.005 sigma by root n. Let's calculate this because this is the 99% CI at this level of significance. You can say alternatively 99% CI for X bar. We will see whether the given value of X bar or the observed value of X bar lies in this interval or not. So let's calculate this. Mu plus minus z 0.005 sigma by root n. Mu is given to you 130 plus minus. Yeah, z 0.005 you can see from the normal distribution table. What is its value? Can somebody tell me? Z 0.005 is how much?
2.58.
2.58. Sigma by root n means 1.5 over root n means root 9. Just simplify it. See what is this interval. I think this interval is, after calculation, 128.712 to 131.29. Take it. What is observed X bar? It is 131.08. Think it like this. This is your interval. 99% CI for X bar, and this is observed value. So X bar is lying in the H naught region. Am I right? Because 131.08 is lying in this interval. So what is your conclusion finally? Can we accept HA or we should not accept HA?
We should not accept HA.
Not accept HA because the observed value of X bar is lying in the H naught region. So not accept S0. Sorry, HA. Alternative hypothesis. Not accept HA. This is the conclusion at 1% level of significance. Can we do the same problem using p-value? Let's calculate p-value also. What is the meaning of p-value? Observing X bar beyond the observed value. What is observed value? 131.08. Because it is symmetric, you can do it 2 times Px bar greater than 131.08. Normal distribution, symmetric. So you can calculate one side and just double it. Can you do it yourself? Because X bar is a normal random variable with mean this 130 and standard deviation sigma 0 equal to 1.5. Just convert it to standard normal variable and do the calculations. In standard normal variable, what is it? Z greater than 2.16. Please check it. And if you use normal table and do the calculations, finally you should get 0.0308. Now tell me, the p-value is less than alpha or greater than alpha? Greater than alpha, right? And once it is greater than alpha, we cannot accept HA. Same conclusion. It gives the same result. So you can do this problem either side. Both way it's fine. Now let me tell you how to calculate type 2 error. This is important. Many students find problems in calculating type 2 error. For calculating type 2 error, some different value of mu would be given to you. Say it is given 131. Suppose actual population mean is not 130, it is 131. But we have not rejected as 0 here because our sample value is lying in the H0 region. So if this is the true population mean, then we have done an error. Let's calculate that. What error we have done and how to calculate that. I told you earlier how to calculate type 2 error. Probability of observing X bar in which interval? In the H0 interval, means this interval. Okay, I should write it in simple way. Probability of observing X bar in which range? 128.712, 131.29. But now when you will convert this to the standard normal variable, because without converting to standard normal variable, you cannot get the probabilities. Then what you will do? 128.71 minus, you will subtract the mean of X bar, but now you will not consider mean of X bar as 130, you will consider the true mean, means 131. Divided by sigma is same, 1.5. Less than equal to X bar minus 131 divided by 1.5, less than equal to, what is it? 131.29 minus 131 divided by 1.5. Now you know this becomes a standard normal variable. You can calculate these probabilities further using the normal distribution table. Okay, this is how we calculate type 2 error. Notice this point, that for converting this into standard normal variable, I have used the true population mean. So this is how we calculate type 2 error. So thing is that probability of observing X bar in the H0 region when the true population mean is 131 is type 2 error. So hope you have understood this problem. Let me do a couple of more problems to understand hypothesis testing further. See the next example in the notes on the same page, on the bottom of page 34. Let's read it. Automotive engineers are using more and more aluminum in manufacturing the automobiles in hopes of reducing the cost and improving the petrol mileage. For a particular model, the mileage on highway has a mean 26 km per liter with a standard deviation of 5 km per liter. It is hoped that a new design manufactured by using more aluminum will increase the mean petrol mileage on highway, maintaining the standard deviation of 5 km per liter. To test this hypothesis, 30 vehicles with new design are tested on highway and the mean petrol mileage is found to be 28.04 km per liter. Find the p-value, interpret it, and decide whether the sample data support the hypothesis of increase in the mean petrol mileage at the 5% level of significance. see what is given and what is to be tested. The claim is on average mileage. So can you design the hypothesis statement? H naught less than equal to 26 and HA greater than 26. Because after using more and more aluminum, it is claimed that average mileage has gone above the previous mileage. So this is, I should write mu also. Mu less than equal to 26, mu greater than 26. So let's say on the basis of the sample information, whether HA can be accepted or not, at which level of significance? 5% level of significance. So see, HA is one side, right-tailed. So this time you need to write upper confidence bound at 5% of level of significance, or you can say 95% CI upper bound. So what is the formula? Can you write yourself? 95% upper bound for x bar, or the observed value of x bar. What is it? Mu plus z.05, I should write z alpha, sigma by root n. Just calculate this thing. Mu is 26. Z 0.05 you can see from the normal table. Check it. What is it? It should be around 1.65. Sigma is how much given to you? 5. And sample size is 36. So 5 over root 36. Calculate it how much it is. It is 27.37. Just tell me in case it is not correct. The calculation is not correct. But what is the observed value in the problem from the sample? X bar observed. It is 28.04. So you see you have a normal distribution. This is the upper 95% bound, 27.37, but the observed value is lying in this region, 28.04. You know this region to the right of the upper bound is your critical region, means HA region. So what can you conclude from this? HA is accepted? Yes or no?
Yes, sir.
Yeah,
Yes, sir.
HA is accepted at the given level of significance. Given level of significance is alpha equal to 0.05, or you can say 5% level of significance. So notice this point. In this case, we are interested in the upper bound. So it is Z alpha is taken here, directly Z 0.05. It is right tail test. You can say it is right tail test. So the whole critical region is on one side. Okay, can you calculate p-value also for this test? Let's verify this result. What is p-value? P-value means probability of X bar greater than the observed value. What is observed value here? 28.04. Let's calculate it. X bar is a normal random variable, so you can change it to Z. So it is Z greater than 2.45 if you do the calculation, considering this mean mu 26 and sigma 5. You see normal distribution table, you will find this value equal to 0.0071. And what is your alpha? 0.05, less than alpha. And once it is less than alpha, you know HA is accepted. So we have done the problem both ways, okay, using critical region test as well as p-value test. Let's do one more problem. Go to page number 35. See the statement there. The example at the bottom of page 35 is the maximum acceptable level for exposure to microwave radiation in Mumbai is an average of 10 microwatts per square centimeter. Assume normality, means population is normal. It is feared that a large television transmitter may be polluting the air nearby by pushing the level of microwave radiation above safe limit. A sample of 25 readings gives an average of 10.3 microwatts per square centimeter with variance 4. This is the sample information. Test the hypothesis whether the transmitter pushes the level of significance beyond the safe limit at alpha equal to 0.1, means 10% level of significance, and also verify it with the p-value. Can you write the hypothesis statement yourself? I think so. This time, this is the prevailing statement about the population. Greater than 10 means the unsafe region. So you want to see whether HA is true or not. At which level of significance? Alpha equal to 0.1. 0.1 means you will calculate 90%. It is one side, you see right side, the right tail test. 90% upper bound for X bar. For upper bound or upper confidence bound, this is proper word. Upper confidence bound for X bar. So 90% means, but one thing you have to note down here, this is normal population, fine. Sample size is what? Less than 30, I think. Yes, it is 25, and also population standard deviation is not given to you. Yeah. Sample is taken from normal population, that is given, but this sigma is not given to you. Standard deviation not given to you. And sample size is small also. So what do you think, which statistic will help you? For which statistic you should find, means which statistic you should use to find 90% upper confidence bound for X bar? I'm waiting for your answer. Yes? Normal population, small sample, standard deviation not given. Which is the suitable test statistic in this case?
Mu plus T alpha S by root n.
No. Which I'm asking the name of the statistic.
T distribution.
Yeah, T distribution is applicable. Okay. Small sample, normal population, and standard deviation not known. In that case, you will use T distribution thing. Okay. So, what should I write here? T 0.90%. So it is 0.1. Yes. T 0.1. And how many degrees of freedom? Sample size is 25, so 24. Then S by root n. S by root n. See your problem. What is S given to you? Mu is 26. T 0.1 for 24 degrees of freedom. You will see from the normal distribution table. Okay. In the not normal distribution table, T distribution table. The value that you will see is 1.318. In the problem, S is given as 2 and N is 25. Just do this calculation, see what they get. You should get 10.527. What is the observed value of X bar given in the statement? It is 10.3. 10.3 is not greater than this, it is less than this. It means your observed statistic is lying in the observed value of X bar is lying in the H0 region. You cannot reject as S0 in this case. Means HA is not accepted. Not accepted. Because the observed value of the test statistic is lying in the H0 region. It is also one side, like this. So the observed value is 10.3, 10.3, and 90% upper confidence bound for X bar is 10.527. So it is left to this, means in the H0 region. Observed value is in the H0 region. That's why HA is not accepted. Now, can you verify the same result using p-value of the test? Find the p-value. P-value means finding probability of X bar greater than the observed value, which is right-tailed, so only greater than 10.3. Just calculate this probability. So naturally, you need to change it to the T distribution variable. So it becomes T24 greater than 0.75. So this you have to check from the T distribution table. In the T distribution table, you will find that this value exactly not available. In that case, you can see values to the left of this and to the right of this. What will you see in the T distribution table? For 24 degrees of freedom, greater than 685, T24 greater than 0.685. This value you can see from the table, it is 0.25. Likewise, probability of T24 greater than 1.138 is 0.1. You can see this value is lying between the two. It means p-value would lie between these two. So you need not to tell the exact p-value, but you can have an idea of the p-value. Means p-value this belongs to this interval 0.25 to 0.1. And what is alpha in your case? Exactly 0.1. It means p-value is less than alpha. P-value less than alpha means HA is not accepted. Okay, so I have explained different problems on hypothesis testing. Now I hope you will be comfortable. Thank you for listening me. And this is the final class.